it has a huge impact on our studies. Like we know we can only convert one form of energy to another. That is, for in our studies, in case of our studies, that is a heat engine case, it will be like converting heat energy to energy, or heat energy to mechanical work is the important thing. So we studied the first law of thermodynamics on a closed system. Okay, so now we are going to study about the second law of thermodynamics, which gives the limitation of how much energy can be converted to another form. Okay, so first law is not at all giving any idea. It states that one form of energy can be converted from another, from one form to the other, but at the same time it is not giving any kind of limitations of that kind of conversions. But in case of second law of thermodynamics, it is giving the uh, limitations of that kind of conversions, energy conversions. Okay, so there are many statements. There are many statements for the second law of thermodynamics. Mainly, we have statements that we are considering. That the first statement is the Kelvin Planck statement, as I have written here. Uh, as I have written here, it's the Kelvin Planck statement. It states that it is important, it is impossible for a heat engine to produce a net work done in a complete cycle if it is exchanging heat only with a single fixed, if it is exchanging heat with a body of a single fixed temperature. That means if the heat engine that we are operating is exchanging heat with a single body, a single body of a fixed temperature, or maybe a multiple body of a, but all the bodies are of a single fixed temperature, only one temperature. If the body, or if the heat engine is exchanging heat with only one temperature, body of single temperature or single fixed temperature, then what happens? It cannot produce work transfer, work done. That is the Kelvin Planck statement. It can be analyzed in, or we can say it in a different way. Okay, so simply for understanding, it is a very difficult statement, as I know. So I'm going to simplify this equation for your understanding. For example, suppose a reservoir, let it this yellow color be a reservoir or a body which is at a high temperature, reservoir or a body at a high temperature, and let be a supply of fuel, a tank that supplies the fuel reservoir. Okay, when burns, it will be at a higher temperature, right? In the engine, when the fuel burns, it will be of high temperature. And since reservoir is something that the supply it remains in the same temperature for infinite time of infinite, for an infinite time. This will be having the same temperature without changing. Okay, that is what is known as a reservoir. Reservoir will be at the same temperature, even though it continuously supplies the heat. It will be at the same temperature for infinite time of infinite time. For example, as we can see, in a vehicle, what we do is that we will go to the pump, we will fill the tank, and it will be acting as a reservoir. It will be continuously supplying the fuel, and when it is almost over, again we will supply the fuel from a tank. So it's somewhat a reservoir, giving some continuously, it is giving the required heat energy to the engine. So it is acting as a reservoir. Okay, and at the other case, that is this reservoir, this reservoir above is giving the heat input actually. So after the production of heat, sorry, work, after the production of work, the engine has to give out the heat, right? So the this heat will be rejected to another reservoir, usually, which is that reservoir, it is our atmosphere, right? Ambient condition, that will be the usual reservoir. That means heat is being continuously dissipated. Vehicles are giving out lot of heat from its body, from its engines, as well as different components of that vehicle. even though the high temperature means what, it is above the ambient temperature or the atmospheric temperature. So what happens, heat is being transferred from that high temperature to the atmosphere, right? Always it will be transferring to the atmosphere. Is the temperature of the atmosphere being increased? No, it is maintaining the almost the same temperature. So we can consider atmosphere as the uh, as the as a reservoir. Okay, so this is another one reservoir at a higher temperature. This yellow color part. I hope you can see my screen. If it is not, please let me know. I'm showing with my pointer, like this one yellow color. It is a reservoir at a high temperature, and this one from which heat is being supplied to the engine. Okay, from the which the heat is being supplied to the engine, and engine is converting this part of heat into work, and remaining part of this QH, a part of QH is being converted to W, and the remaining part of the QH is rejected as QL. QL is the heat rejected. Okay, it is we can consider it as the heat rejected by through the other parts of the body or the engine to the atmosphere. Okay, QL will be rejected to the atmosphere. Atmosphere is the second reservoir at a lower temperature. So TH is a high temperature, or THH means high. TH is a higher temperature. TL is the low temperature. QH is considered as the heat supplied, and QL is the heat rejected by the engine, and W is the net work produced by the engine. Hope you understand this concept. So we are moving to the Kelvin Planck statement. So Kelvin Planck statement, as per the Kelvin Planck statement, if this QL is not here, for example, if it is like this, reservoir at a temperature TH, or T, let it be T, no high temperature, right? Only one single temperature is there. So it's a single body or a reservoir with a higher temperature is exchanging heat with the engine. That means from T, Q is given to the W. Then W can't produce sorry, this engine can't produce W. That is what Kelvin Planck is stating. That is, if this engine is exchanging heat with the single body, that means Q is being supplied from the reservoir to the engine, and that heat cannot be completely converted to W. I mean, not completely converted, that heat cannot be converted to W. That is what is Kelvin Planck is stating. That means another term, in another way, there should be a heat rejection. There should be always a heat rejection. Okay, so if a heat is being converted to W, that is, if a part of QH is being converted to W, then there should be a heat rejection QL. Always it should be greater than 0. QL should be always greater than 0. That is what Kelvin statement is saying. So in another words, again in another words, we can say no heat engine can have 100% efficiency. What is efficiency? What is efficiency? Anyone know? What is an efficiency? What is the efficiency? Anyone? Anyone is listening? Hello? Hello? Okay, no,
Yes,
no,
yes.
no. Oh, okay. So in other words, we can say that no heat engine can have 100% efficiency. So efficiency, what is an efficiency? Efficiency is the output by input. So we can say this is also, W is also an output. QL is also an output, right? Engine is giving out W and is also rejecting the QL. Then how can we write W by QH here? Output by input as W by QH. QL also come here, right? So efficiency is always calculated in terms of required output. Whatever output is required for us, that is being taken as output. So from a heat engine, we will be always calculating work as output, right? Not QL. If we can convert QL also to W, we will try to convert. But by the first law, it is not possible. Sorry, second law, it is not possible. So W work that is being given out of the engine divided by the heat input. That is what is known as the efficiency of the engine. Right. Right. Required output is W, work output. and input is the QH, heat supplied. So W by QH is the work efficiency of that engine. So this efficiency cannot be 100%. That means QH never is equal to, when will it be 100%? When W is equal to QH, it will be, we can cancel both of them, right? Then it will become unity 1. That means it will be giving 100% of efficiency. It is not possible. That's what is that is what Kelvin's Planck is stating. So so W will be always less than QH, or the heat supplied. So again, we can write it as W. What is W? W is the heat, and it is a form of energy. W is also a form of energy. So how can, if from this picture itself, we can say it is a QH is a heat supplied. W and QL is the heat rejected. I mean, sorry, energy rejected by the engine, or given output of this engine. So QH will be always equal to W plus QL, right? QH is always equal to W plus QL. QH is equal to, or heat supplied is equal to heat rejected plus work output. So from that equation, we can write as W is W equal to what? QH minus QL. That is what is written here. W will be equal to heat supplied minus heat rejected. That difference of the energy will be equal to the work done. That is what is being written here. Please note down this equation, because this will be used here and there, so that we can solve the problems. It's a very important equation if you are going for a gate and all. It's a very simple equation, but it will be used here and there for finding problems. Okay, simple problems only. Okay. So again, I'm telling that Kelvin Planck statement is states that um, what a heat engine cannot produce a work done. A heat engine cannot produce a work done by exchanging heat with a single of a body of single fixed temperature, or fixed single fixed this engine cannot produce a work done by exchanging heat with a single fixed temperature. Okay. So again, and we came to another statement, like no engine can have a 100% efficiency, because it should always exchange with the exchange heat with the two bodies of different temperatures. Then only it can produce a work done. So okay. So as we studied PMM1, we studied in the first law of thermodynamics, the PMM1. What is known as, it is known as the perpetual motion machine of kind 1, right? What was that? That body or that engine was producing heat or a work without any input, right? A heat, sorry, a body that is producing work without a heat input. That was PMM1. That is, it is creating some kind of energy. It opposes the first law of thermodynamics. Or it will take the work without any heat output or any kind of output in a cycle. That means it is destroying some kind of energy. That was PMM1. So PMM2, or perpetual motion machine of kind 2, is also another type of imaginary heat engine, which is against the second law of thermodynamics, which opposes the first law, second law of thermodynamics. PMM2 opposes the second law of thermodynamics, or the Kelvin Planck statement. Okay, so it is an engine which operates in a cycle. Okay, it's an engine, imaginary engine operating in a cycle, which is receiving heat from a body of single fixed temperature. This engine is receiving heat from a body or reservoir of single fixed temperature T. This T is exchanging heat only with a single fixed temperature, or it is receiving the heat from a body and is completely giving out it as work output, right? So if it obeys the Kelvin Planck statement, what it should do, some heat should be rejected to some other body. If it is Q, some QL or Q1 should be rejected to another reservoir of a different temperature. So it is it is against the second law of thermodynamics. So what will be the efficiency? Of course, we know as per the Kelvin-Planck statement, for any engine, the efficiency should be less than 100%, right? In energy efficiency should be always less than 100%. But for in case of the PMM2, as it is against the second law of thermodynamics or Kelvin-Planck statement, it will be giving out 100% of efficiency. That is, efficiency is equal to output by input, that is W by QH. Here Q is taken and it is completely converted to W. So QH will be equal to W, right? This Q is taken in and is converted to W completely. So W will be equal to Q. So output by input will be equal to 1. That means it is giving output, giving a output of 100%. Okay, I hope you got that. So it is violating the second law of thermodynamics. So we will do a problem. Find the efficiency of a heat engine which receives 60 kilojoule of heat and rejects 20 kilojoule of heat. That means what? Find the efficiency of a heat engine which receives 60 kilojoule of heat and rejects 20 kilojoule of heat. That means this is a heat engine, is the heat engine. It is receiving 60 kilojoule. That means QH will be equal to 60 kilojoule, right? QH will be equal to 60 kilojoule and QL heat rejected is equal to 20 kilojoule. That is QL is equal to 20 kilojoule. So simply, what is the efficiency? Efficiency is work output by input, right? Work output, how can we find the work output? It is the exchange of energies, so or conversion of energies. So W will be equal to QH minus QL. Work will be equal to QH minus QL, as we studied in the previous slide. It will be QH minus QL by divided by denominator will be output, input will be QH. So we can directly substitute the values and we'll be getting the efficiency, that is heat rejected QH is equal to 60, Q L is equal to 20 and divided by input, that is 60 into 100, that will be 66.7% will be the efficiency of heat engine. Hope you got the problem. Okay, let's move. Hello.
Yes, sir.
Yes, you
Okay.
Go ahead.
Okay. So
Sir,
next we will be moving to okay.
Past
Next
slide, sir.
Okay. Next we will be moving to the Carnot's theorem. Okay, so we are getting into so now we are getting to the basics of working of the heat engine, So we will start with the Carnot's theorem. So before knowing a Carnot's theorem, we have to understand what is a reversible process in a what is a reversible process. Okay, reversible process is there is a lot of more, you have to know a lot more about the reversible process. I'm not going to explain a lot of things, but the basics of a reversible process. Okay, so simply reversible process is a process if it is reversed. If suppose A to B is a process, for example, if heat is being flown from a high temperature to a lower temperature, or a body rejects some heat, then what happens? The body will undergo a process. Okay, suppose a body is rejecting some heat, then the body will be undergoing a process. So A to B can be considered as a process. So if we are reversing this process, that means from we are supplying some heat to, in same way we are supplying heat to that body. That means we are reversing from B to A, we are reversing the process, and the system and surroundings are restored to the initial conditions. System and surround, we can say system means that body. If that body and its surroundings, that means the entire things around that are restored to the initial state, that is state A, then we can call it as a reversible process. That means if a process A to B is done, and if we are reversing that process, reversing that process means the process being converted from moved from B to A in the same path. Through the same path, it is being converted to A, and at A, if the system or the body and its surroundings are restored, then it is known as a reversible process. Okay, so is there any reversible process in this world? Nothing. Nothing is, no natural process is a reversible process. Okay, for example, water is being flown from high altitude to the low altitude. Water will be always flowing from the high altitude to the lower altitude. If we want to reverse that, we have to use a pump or some similar devices to pump from the lower potential to the higher potential, or heat will be always flowing from high temperature to low temperature. If we want to reverse, we will have to give additional work to pump it to the pump the temperature, I mean heat from lower temperature to the higher temperature. So in that case also, there are some the concept is that it is the system may be restored, or the when the heat is pumped from a lower temperature to higher temperature, as in the initial case. For example, from body, let A be a body from which heat is pumped out and is reached to the condition B, and from this condition it is we are pumping back into the body and is reaching A. The body may be restored. At the same time, the nature or the surroundings will be having some other effect in some other effects will be there around the around that body. I'm making a short, a lot of more things like entropy things will be there to study. So I'm trying to avoid that concepts and all. So it is difficult to explain also. So if I say it simply, if we are doing a process against a natural process, okay, if we are doing a process against the natural process and restoring the body then there will be changes around the outside that of that body. Outside that body, there will be some changes. That surroundings won't be restored to the initial condition. Okay, the surroundings won't be restored to the initial condition. So there is no natural process, or there is no actual reversible process. There won't be any actual reversible process. Okay, so that is a concept. So so that is a reversible process. So we are going to study the Carnot's theorem next. Okay, so Carnot's theorem states that a reversible engine, if we are making a engine which is operating in a cycle, if we are making a reversible engine operating in a cycle, which all the processes are reversible, in which all the processes are reversible, then what it that engine will be having the maximum efficiency. Okay, so why Carnot's theorem is important is that Carnot's theorem is giving an idea of how much maximum work can be produced from an engine. Okay, so Carnot is stating like is stating that of all heat engines operating between constant temperature sources, none has a higher efficiency than a reversible heat engine. That means if we are making a engine with all the process as a reversible process, if all the process are a reversible process, then that engine will be having the maximum efficiency. Hello? Hello? You are get hello.
Yeah, go ahead, please.
Yes,
Okay.
yes, go ahead.
Okay, Carnot's theorem states that. Okay, again I will be telling you that. Hope you understood what is a reversible process. Reversible process. What is that? Reversible process is a process which can be reversed through its path, such that the system and surroundings are restored to the initial condition. Okay, system restored to the initial condition. So if we are making a engine which is operating in a cycle in which all the processes are reversible. Okay, we are making an engine which is operating in a cycle and all the process in that cycle are reversible. Then that kind of engine will be producing the maximum possible output. That means maximum work output, or we can say maximum efficiency. Okay, that kind of engine will be giving the maximum efficiency considered to all the other irreversible engines or the normal engines operating in the same temperatures. So I will explain it again. Here I have shown two engines. One is a reversible engine. So this is a reversible engine, and this one is an irreversible engine. Okay, this is a reversible engine, and this is an irreversible engine. Reversible engine means all the process. This engine operates is operating in a reversible cycle. Reversible cycle means all the process in that cycle is a reversible process. Hope you are getting. That means we can reverse that from the next diagram. We will understand again. So just listen to here. Uh, this engine is operating between two temperatures TH and TL, and this is a reversible engine. This is a reversible engine. So it will be taking a heat input of QH and will be giving a work output of W max. Okay, work output of W max, and will be rejecting QLR, rejecting QLR. Okay, this will be receiving QH, converting a part of QH as W max or work output, maximum work output, and will be rejecting a heat of QLR to uh, another reservoir. We can say atmosphere. So we are considering another engine E, which is which we can call is a irreversible engine, which we can call a irreversible engine. Irreversible engine means it is also operating in a cycle, but all the process, all the process or any of the process are reversible. None of the process are reversible, or we can't reverse this process, or we can't receive give QL and W and produce QH in that. It's operating in a natural conditions. Okay, this is a natural engine or irreversible engine which cannot be reversed easily. Okay, so this engine or a irreversible engine will always be producing a work output less than that of this engine. This engine will be producing always a work output less than that of this one, or W will be always less than W max. Hope you are understanding. For both these engines, this TH is equal, or the upper temperature is equal, and lower temperature is also equal, or TL of for both the engines are equal. But the difference is that this is a reversible engine and this one is an irreversible engine. So reversible, as per the Carnot's theorem of two, if we are considering two engines, one reversible and another irreversible engine, reversible engine will be always having a higher work output or higher efficiency than all other engines. Like this, how many engines if you make also, although the output of these engines will be less than that of a reversible engine. So this will be W max will be always greater than W. Okay, so that is what is a Carnot's theorem. Okay, so I have modified some of the equations here. So as per our previous second law of thermodynamics, we have the equation like efficiency of a reversible engine, or we can be written, or we can write it as a common equation for reversible and irreversible engine. So efficiency of irreversible will be equal to W by QH. We have studied that earlier, right? That is also equal to W can be written as QH minus QL. So QH minus QL by QH. We can write like that. And coming to coming to a reversible engine, we can say write the same equation. Okay, efficiency or eta reversible will be equal to W max by QH, which is equal to W max can be written as QH minus QLR. QH minus QLR divided by QH. Input is QH. Again, when we study further in thermodynamics, we can find that this Q is always a function of T. This QH is also always a function of TH, and QLR is always a function of TL, or we can say they are directly proportional. This one is also okay. QH is directly proportional to TH, like that we can say, or QH is always a function of TH, and QLR is also always a function of TL. TH means higher temperature, and TL is a lower temperature. So we can write TH minus T instead of this one. We can write TH minus TL by TH. T is the temperature. TH is the higher temperature, and TL is the lower temperature. So we can use this equation also for a reversible engine only. Not done like this is an equation for reversible engine only. For irreversible engines, all the engines will be operating differently, right? We all know, if you are considering different engines of a different of the same vehicle. For example, if we are taking bikes, any particular bike, a model, if we are taking a particular model of the bike, even though if it is of a particular model or a particular vehicle, the engine efficiencies vary for various vehicles, right? So one will be giving 60 percentage of or one will be having high work output, even with the very less fuel also it will be giving, or we can say in other terms, we can say one vehicle will be giving 65 kilometers of mileage. At the same time, the same vehicle having of a front will be having a different mileage, right? So there is difference between the irreversible engines. So we can't perfectly say that QH or QL is a function of TH and TL. So we can't write TH minus TL by TH for a reversible engine in case of a reversible, or it will be having some other losses like friction or something. So we can't write it directly. Okay. So this is a equation, efficiency equation for an irreversible engine. It stops here, but a reversible engine we can write. The process is reversible. All the processes are reversible. So the QH and QLR will be proportional to the TH and TL given. So we can write TH minus TL by TH. So I have listed this like here. Eta reversible will be always greater than eta irreversible. That as I stated earlier, that means maximum work output will be always greater than W. Hope you understand the concept. So we will be moving to Carnot cycle. So Carnot cycle is a conceptual cycle. As I said, no natural process is a reversible process. As I said, no natural process is a reversible process. So it's a Carnot cycle. Carnot cycle is also a conceptual cycle. So Carnot cycle is also a conceptual cycle. You can see. Okay. And so hold on a second. So Carnot cycle is a conceptual cycle which is giving which is having all the process as reversible process. So all the process in this cycle will be having a reversible process. As I said, what is a cycle? A cycle is a series of processes cycle is a series of processes in which the after all the process it will return to the initial state, or the system or the body or the engine will return to the initial state. That means if the engine starts a process from 1, it will reach 2 in a state 2 in through a reversible process, and from 2 to 3 in another reversible process, and from 3 to 4 in another reversible process, and from 4 to 1 or the initial condition, it will come to the initial condition again. It repeats, the cycle repeats. That is what is known as a cyclic process. So for a Carnot cycle, or for a Carnot cycle, all these processes will be a reversible process, or 1 to 2 will be a reversible process, 2 to 3 will be another reversible process, 3 to 4 will be another reversible process, and 4 to 1 will be another reversible process. And hence it is a hypothetical engine, or it's a engine that is not possible actually. So why we are studying this cycle is that we have to design engines where the losses are minimum, or losses are minimum such a way that it gives an efficiency somewhat near to this engine. Okay, we will be trying to create engines, or trying to build engine or design the engines such that the efficiency comes more closer to the Carnot's engine, or sorry, Carnot's cycle. That means why? Because this is the maximum possible efficiency. This cycle gives the maximum possible efficiency that can be given out by any engine operating in that temperature limits. Okay. So let's go into more deep into the Carnot cycle. So Carnot cycle, as I said, again, I'm telling you that all the processes are reversible process. Within that, it consists of two isothermal processes, 1 to 2 and 3 to 4, and two adiabatic processes, that is 2 to 3 and 4 to 1. So what is isothermal, or what is adiabatic process? So that is what is I have shown in these two figures. So isothermal process is a process in which temperature remains constant. Okay, in that process, when a process is happening, the temperature remains constant. So what is an adiabatic process? Adiabatic process is a process in which the heat content in that process is a constant. Heat content in that process is a constant. That is what is known as adiabatic. So what is the difference? We are both using adiabatic and isothermal as same, right? Heat and temperature, we all related problem. Then how it changes? If it is adiabatic, it should be isothermal, right? And isothermal, it should be adiabatic, right? What is the difference? So we will first discuss that. So we are representing this one isothermal process here. Isothermal process can or cannot be a adiabatic process. Okay, that is the first condition. That means, suppose if it is uh, we can see a piston cylinder arrangement here, right? Like a syringe, we can say a cylinder and a piston here. Suppose that some gases are inside this area. If it is this side is also closed, the bottom portion is also closed of this cylinder, and that means this gas is contained in this cylinder as well as the bottom portion of this piston arrangement. So the mass cannot flow out, right? The gas cannot flow out. It is constrained within this area, this volume below the piston and within this walls of the cylinder. Okay, so thing like we are supplying some heat. Suppose this colored portion, this orange colored portion is a hot area. Okay, if it is a hot area, what happens? Heat will automatically flow from this area to this volume, or to this gas, right? So what happens? Heat is supplied. Heat is what? Heat is a form of energy. That form of energy is supplied to the gas here. Then what happens? Heat will heat will be as the heat is provided, automatically what happens? Temperature will rise. So how will we keep it as isothermal? Isothermal means constant temperature process. So how will we keep it as a isothermal process? We need to move this piston up. While moving this piston up, what happens is that pressure reduces as well as volume increases. Okay, pressure will be reduced and volume will be pressure will be reduced and the volume will be increased. By that way, we will try to keep the same temperature in that within that volume. That means while supplying heat, we will be moving the piston out, or while removing the heat in the reverse case. While removing the heat, if this system is moving to this ice block, this will be a low temperature, right? Then heat will be flowing from the cylinder or from the gas to the will be flowing from the gas to the hello hello okay, from the gas to the ice, right? So the reverse case, when it is hot, heat will flow inside. When it is cold, heat will flow outside. So in that process, for keeping the temperature constant, what will we do is that we will move the piston in or out. Okay, if the piston is moving in or out, that means that is what we are calling a mechanical work, right? When the piston is moving in or out, we can call it as a mechanical work. So isothermal process will be always will be always of a closed system will be always accompanied by a work input or a work output. So here will be always accompanied by work input, work output, or also heat input or heat output. Both can happen, right? So here to keep that temperature constant, while heat supplying, the piston is moving up, so work is also giving out. So here also, what is happening is that by cooling, piston has to come down while giving out the heat to keep the temperature constant. So work is also happening. That also what is happening? Heat is also given out. So isothermal can be both accompanied by heat transfer as well as work transfer. Okay. So here what we have taken is a heat transfer condition. So heat input will be given in this isothermal process 1 to 2. The heat input will be given in. And to 2 to 3, it is an adiabatic process. So adiabatic, so we explained about an isothermal process. Then what is adiabatic process? Adiabatic process is a process in which no heat energy will comes out of the system. Here what was happening in isothermal process, heat was giving an input as an input, and also heat was giving as an output in the other case. Here what is happening is that there is no energy flow in terms of heat energy flow into the system or out of the system. The heat, whatever the energy contained as heat, will be within that system in that process. Okay, that is what is known as adiabatic process. Hope you got the difference between adiabatic and isothermal process. So in a Carnot's theorem, Carnot cycle, in a Carnot cycle, four processes will be there. Four processes will be there. Two will be isothermal, two will be isothermal, and two will be adiabatic. So adiabatic process, that is 1 to 2 is the first process where the heat is given as an input, and in adiabatic process or 2 to 3, there will be a work output. There will be a work output, and 3 to 4, it will be a heat output. I mean, heat will be rejected in case of 3 to 4 or a isothermal process, and 4 to 1 in the adiabatic process, work will be given into the system. I will explain the next slide. You will get that. So it will be the process that is 1 to 2 is a isothermal heat input. 2 to 3, work output will be given, a work output, no heat transfer, only a work output will be given. And 3 to 4, there will be heat output or heat is rejected by the system. And 4 to 1, it will be a adiabatic process where a work input will be given. So the net work output will be the net output work output of the system. Entire cycle will be equal to whatever heat is work is rejected or work is given out in the 2 to 3 processes minus whatever the work is given into the cycle in 4 to 1 process. As I said, 2 to 3 there is a work output, and in 4 to 1 there is a work input. I am not marked here, I will mark here. So here there will be a work output, and here there will be a work input, wi. So the net work output will be is equal to net work output in is equal to work output minus work input. That will be the area within this curve. So whatever heat work is given out minus whatever the work is given input will be the network output. Okay. So a simple system is represented here, where it is showing two systems, or isothermal process and one adiabatic process, and one isothermal process, and again adiabatic process. How the engine works in that cycle, the imaginary engine working in that cycle is almost represented here. It's not the exact thing, but it is represented here. Okay. So this is the network. Whatever the work input is given, that will be reduced from whatever the work output is given. That will be the next net work output. So this is a Carnot engine. Carnot engine is an engine which works on the on based on the Carnot cycle. Carnot engine is an engine which works on based on a Carnot cycle. So this is how the engine works. Suppose this be a steam engine, like there will be heat exchanger here. This is a heat exchanger here, where we can call it as a boiler. Okay, in case of a steam turbine, we can call it as a boiler. Where in the beginning of the class, I have shown you how a steam engine was working. But there we will be burning coal in a chamber, and the heat will be transferred to a boiler, and there where the water is being boiled, and that boiled water which is turned into a steam is passed through a turbine to rotate the turbine, right? But at the same time, whatever the steam formed, and as well as the exhaust gas was passed through a tunnel which is given out of the system, which works as an open system. But here what it's a closed system, where from the source, some heating source, maybe a coal, burning of a coal, maybe burning of some other fuels, which heats up the working fluid. Maybe we can call it as steam. Okay, it may be any kind. Okay, it may be let us call it as a steam. As a this one is a steam turbine. So steam will be produced here, as we learned earlier, and that steam will pass into a turbine. This is a turbine B. B is a turbine. Here it is it is a turbine. Okay, so 1 to 2 is the process. 1 to 2 was what? 1 to 2 in the cycle. 1 to 2 was a isothermal heat input process. So in this process, in the boiling process, what happens is there is no it is considered as a isothermal process. Temperature there won't be temperature rise, but heat is being supplied there. 1 to 2 process we have marked here. So we are supplying heat, but without raising the temperature. So it's a isothermal process. So from there, it is passing through 2 to 3 or 2 to 3, which is an adiabatic process, where there is no heat rejection. But what is giving out? We will be having a work output. Turbine will be producing work, right? We know what is a turbine. So while passing through the turbine, the steam passing through a turbine, it will give us a work output. So here we are creating a work output. WT, it is marked as WT. So 2 to 3 process is over. Here 2 to 3 processes here where we are getting a WT. WT means the work done by the turbine. This is a work output. Then what will happen to the working fluid? From 3 to 4, it will pass through another heat exchanger. Here what is happening is that this heat exchanger will be at a, this working fluid will be at a higher temperature. This and thus what happens, since it is in a higher temperature, it will be giving out its heat to another sink. Sink means it is also a reservoir where a low temperature is maintained. Okay, so it is the working fluid after the working fluid which is coming out of the turbine. The working fluid which is coming out of the turbine will be having a higher temperature than than this sink, or we can say it is a cooling water or something. Okay, it is a cooling water. So it will this cooling water will be having a low temperature compared to the working fluid. So what happens? This working fluid will reject heat into this, or Q2 will be rejected. Or we can say it is a isothermal heat rejection process 3 to 4. It is also marked as 3 to 4. Okay, then again 4 to 1. 4 to 1 is a compressor or pump. We can say here, since we are considering it as a steam turbine, while rejecting heat here, it will be converted to liquid again or water again. So this water in the sum will be pumped back to the boiler through a pump. We have to pump it back. Since it is a liquid, we have to pump it back. So this pump will be taking, so operating a pump, it will be taking a work input, right? It requires a work input, but this work input will be lesser than that of WT, or the work produced by the turbine will be higher than that of the pump that we are operating here. So what we will do is that the work needed for this pump will be taken out of WT, or the heat engine. Sorry, or the turbine. WT is higher than that of WP, so WP will be taken out of WT. From this turbine, from the turbine, work output will be given. From that WT, we will take what? WP for operating this pump. So what will be the net work output? Net work output will be equal to WT minus WP. Work given out by the turbine minus work input to the pump. That will be the net work output. Okay. So again, it comes to the state 1, or state 1. This will be WP. Or the pumping process will be is considered to be adiabatic. Okay. Hope you got the working of this cycle, or this engine. So I will be telling you again that here is a boiler which boils the water by taking heat, and this process will be isothermal process, isothermal heat addition process. 1 to 2 is a isothermal heat addition process where boiler boils its water to steam, and from 2 to 3 it's a adiabatic work output process, a process which is giving the work output by passing this steam through a turbine. The turbine is rotated and we will be getting a work output WT, and that is a 2 to 3. It is also a reversible process and is an adiabatic process. From 3 to 4, from 3 to 4, it is a heat rejection process where the working fluid is cooled to cooled back to the fluid or water from the steam. From the steam, this will be converting back to water here, and the rejection process will be a isothermal process. 3 to 4 will be an isothermal process I have indicated here, but at the same time it will be rejecting the heat. And 4 to 1, 4 to 1 will be a pumping process. Water is to be pumped back to the source, back to the boiler, and this requires work input, and work input for operating this pump will be taken from work output of the turbine. So the net work output will be WT minus WP. So in the other case, as I said, this is all a reversible process in which all these process can be reversed, which is represented here. This is a reversible engine. So here what is happening is that I said this is a hypothetical concept. So don't think that we can pump back heat back to the higher temperature. Anyway, we will be telling like it is a reversible process in which the process can be entire process 1 2 3 4 can be reversed as 4 3 2 1. Okay, this 4 3 2 1 it can be reversed. So we will be from here it will be pumping the working fluid back to heat exchanger here, where heat will be taken from the source, or we can say if in a natural process it is not possible from taking heat from a lower temperature body to high temperature body. So it is not possible actually. So as it is a hypothetical process for comparison of the real engines we'll be considering it. So this engine will be giving a maximum efficiency, so we'll be considering like this. Okay, so so this reverse like the pump will be taking pumping back by producing, or water will be coming through the pump and pump will be producing the work output WP, and here it will receive heat from a low temperature body coming back here. Turbine will act as a pump here, will be pumping working fluid from here to here, and here what is happening is that heat will be rejected to a high temperature body. So the entire thing is reversed. So this kind of an engine is called a reversible engine. And if the reversible engine is operating between these conditions, that is two isothermal and adiabatic processes, then it is known as a Carnot engine. Okay, so it's simplified. These all things are simplified here. That means this turbine and pump is being combined here in both the cases. Okay, so here what is happening is that the heat is being received from a high temperature body, that is QT is being received from a higher temperature body, and will be creating a net work output. Net work output means WT minus WP. WT minus WP is the net work output. It is combined here. So it is giving a net work output of WT minus WP and is rejecting heat to a temperature of T2. And in the reverse case, here from the lower temperature body, QT is being taken, and what is happening is that it will be rejecting or a net work input is required. Since WT is higher, what will happen? What will happen? WP, if we are taking WP as positive, since it is giving a work output, WP is giving us a work output. What will happen? It is taken as positive, right? And WT is taken as negative since it's a work input. So WP minus WT will be always be negative. Okay, WP minus WT. WT will be always higher and WP will be always less, as I said. So this difference will be negative. That means the net work input will be given. W net will be negative. That means it is a work input, and this system will give out a heat of QT to the temperature T1. Hope you got a basic idea. I hope you have got a basic idea. Then we will move on to next portion. Okay. Any doubt in this?
No, sir. No, sir.
No,
Okay.
sir. Clear, clear.
Okay. So we'll be doing a problem for this. Okay, we will be doing a problem. We will be making it fast because already time is over. So a cyclic heat engine operates between source temperature of 800 degrees Celsius and a sink temperature of 30 degrees Celsius. So we have a higher temperature 800 degrees Celsius and a sink temperature, lower temperature 30 degrees Celsius. What is the lowest possible rate of heat rejection per kilowatt net output of the engine? We have to understand a lot of things here. So first one is the temperature. We have given a higher temperature and a lower temperature. So the engine will be operating in these two temperatures, 800 degrees Celsius and 30 degrees Celsius, right? And the question is that what is the lowest possible rate of heat rejection? Lowest possible rate of heat rejection. Okay, that is minimum heat rejected. Or QL should be what? It should be minimum. QL should be minimum, right? Then one more condition for finding the work output, one case is given here per kilowatt of net output. Per kilowatt of net output എന്നാണ് പറഞ്ഞത്. It's said. It's like it said like per kilowatt of net output. What does that mean? The work output is 1 kilowatt, right? We have to consider that for 1 kilowatt of work output, net work output means what? Required output is what? Work only, right? Even though there are two output for the engine, that is W and QL, what will we have to consider? We have to consider W. W is the required work output, required output for that engine. So when we are saying that per kilowatt net output means we have to consider this net output as work done. Okay. So per means what? 1 kilowatt of heat work output. What is the heat rejected? That is the question. Okay. And one more thing is that it is a minimum possible heat rejected. Like that it is asked. Right. So where will be the minimum heat rejected? In which condition the minimum heat is rejected? It will be in case of a reversible engine, right? Heat will be rejected as a minimum quantity in case of a reversible engine only. We have studied the Carnot's theorem. As per the Carnot's theorem, a reversible engine is having the highest possible efficiency while operating between while operating between two temperature limits, right? It is having the highest efficiency. Highest efficiency means what? The maximum heat that is being converted to work. That means what? Minimum heat rejected, right? Hope you are understanding. Reversible engines are having the maximum possible efficiency. Efficiency means what? Maximum heat input or QH, maximum part of the QH is converted to W. That means what? Heat is rejected as minimum, right? So the condition is possible. This condition, lowest possible heat rejection is what is happening in a reversible engine. Hope you are getting that. Okay, so QL will be minimum or heat rejected will be minimum in a reversible process. I'm telling this because we can take this equation. Okay, reversible equation engine, for a reversible engine, efficiency can be written as TH minus TL by TH. Right, right. TH minus TL by TH. We can. I told you QH and QR or QL is a function of TH and TL. So of course we can write this, we can replace this QH minus QLR divided by QH as TH minus TL by TH. I have written here in the previous equation. Here I have written that the same equation, efficiency is same equation. But the thing is that you have to identify that this is a reversible engine. Minimum heat rejection is possible in the reversible heat engine. That is the condition that you have to remember. Then you can apply this equation. Okay, efficiency max is equal to TH minus TL by TH. So simply we can put the values of heat temperature limits. That is higher temperature and lower temperature. That is 800 by 800 is the input. I mean the higher temperature. So 800 plus 273. 273 is for converting this degree. It is in degree Celsius. So for converting it into Kelvin scale, will be adding 273. Here also it is in degree Celsius. So 73 is added to make it into Kelvin scale. So it will be 1 minus TL. TL will be lower temperature, that is of the sink, temperature of the sink, and this one will be of that of the source. So 1 minus applying this equation will be getting 0.718 or 71.8 percentage as efficiency. 71.8 as the efficiency. So we got the efficiency. So if we have the efficiency, again we can write this equation, right? We can take this equation, the efficiency is equal to W max by QH. From that we will get W max. QH is already sorry.
Sorry
W
for
max is
interrupting. The session will get expired in too few seconds. The session will get expired because it's 8:15 was the final timing
okay.
that was given.
Okay, okay. Just a second. I will be just apply this one. W max is 1. Just applied here, and QH will be given as 1 by efficiencies. We have found the efficiency here. So QH will be equal to 1 by 0.718. That is equal to 1.392 kilowatt. That is the QH. So QL can be found out as a difference between QH minus QNet. QNet is the net work output. It's a 1. QH is found out. We have found the QH here. So QH minus W net, that is the total. Minimum heat rejected, that is 0.392 kilowatt. Hope you got this. We will meet in the next class. Thank you.